Welcome back to this afternoon session. We are now going to have some short talks, 20 minutes approximately, and our first speaker is Dhruv Bhasin from Pune, who will tell us about bond percolation games and their connections to probabilistic cellular automata.
Thank you. Good evening, everyone. I would like to begin by thanking the organizers for giving me this opportunity to speak here. Oh, can you hear me? Fine. Okay. So, yes. Today, what I'm going to talk about percolation games and their connections to probabilistic cellular automata (PCAs), and this is joint work with Professor Kormakar, Professor Bodwar, and Professor Roy. So there are two players to this talk, percolation games and probabilistic cellular automata. I would begin by describing percolation games. Well, percolation is a process which we think of as a process on Z2. And usually what happens is we have a real number, P between 0 and 1. And there are two types of percolation usually studied, side percolation, bond percolation. And for side percolation, we declare a vertex to be open with probability P, otherwise closed with probability 1 minus P. And the question people usually ask is there an infinite cluster of open sites or open vertices? So for example, in some way, the question is that is there an infinite path of open sites? Similarly, for bond percolation, the edges or the bonds are declared to be closed or open with probability P and 1 minus P respectively. And in both cases, it is known that beyond a critical probability, there is always an open infinite cluster. And we are going to talk about percolation games, which were first studied in this paper by Professor Holroyd, Professor Markovici, and Professor Martin. The setup is as follows, that we have Z2, and we have two real numbers now, P and Q, such that P plus Q, this parameter is less than or equal to 1. This P plus Q in some ways behaves like the earlier P. And we declare a vertex to be trap with probability P, target with probability Q, and open with probability 1 minus P minus Q. That is, we roll a three-sided die at every vertex, and if trap shows up with probability P, we declare it to be a trap, and so on. And the game is as follows. Once this random process has happened, a realization of it is fed to two players. So two players play on this random board. This is an example of such a board. The red crosses are traps, the white squares are targets, and this orange at the origin is the token. Now two players, me and you, will play a game on this random board. What will happen is, suppose I go first, then I can move the token either to east or north. So if the token is at a vertex X, it can be moved to X plus E1 or X plus E2 alternatively. And if I am able to move the token to a target, I win. Or if I am able to force you to move the token to a trap, I win. And the same goes for you. And if the game continues forever, it is declared to be a draw. So this is the setup of this paper. And let us for this talk call this a side percolation game on Z2. Now, the question red in this case is the trap, in this P.
To a trap, you win.
No, if I move to a target, I win.
Target is
White, yes.
So target is white square.
Yes, white square.
And so if you move to a white square, you win.
Yes.
Or if the opponent moves to a
Trap.
red cross, again you win.
Yes.
Yeah. Thank you.
Thank you. Yeah. And the black squares are open, so the game can go along black squares. And the question which was asked is, what is the probability that the side percolation game results in a draw? And if you think about it, suppose the game results in a draw, then the players would have played the game along an infinite path. So this is a way the game ties, this question ties with the theory of percolation. And the result which these authors obtained is that for any parameter P and Q, such that the tuple P and Q is non-zero, the side percolation game always has the probability of draw to be exactly 0. And if you think about it, for me, this result is quite surprising, because if P and Q were very small, like 10 to the power minus 100, it says that in the random board which is obtained, there are very few traps and very few targets. Even then the game results in a draw. even then there is a result. There is no probability of draw. And they used, to prove this result, they used relations to probabilistic cellular automata. Cellular automata were introduced by Stanislaw Olom and John von Neumann in 1940s, and they are used everywhere. I think we saw one in morning's talk. The setup of a cellular automata, so for these purposes, we are only looking at one-dimensional CS. So that is, we have the strip Z, and we want to put alphabets on it. We will come to it. The alphabet set is any finite set. For us, it will be just WLD. I will explain what that means. And to describe a CA, one also needs a neighborhood, a tuple y1 through ym, where m is a parameter of the CA again, and a set of rules which tell that given a state eta, sorry, this should be e to the z. So that is, eta is strip Z with alphabets filled up on it. A CA should tell how to go to the next state. And the way it will do it is, it will tell the next state of the xth entry by looking at the current states of x plus y1 x plus ym. This needs refining, yep. So that's the setup of a CA. And if the rules are probabilistic in nature, then we call it to be a PCA. So if the vertices where we are looking at, if it results in a probability distribution, then we call it to be a PCA. Now, in the next few slides, I want to demonstrate how in the game one can really think of a PCA. So let us come back to the lattice Z2. I have removed the traps and targets for now for better visualization. Let us look at this diagonal, any diagonal, a fixed one. And the claim is that suppose we know the results along this diagonal. That is, suppose we know that, suppose the token was placed here and then the game is played. What is the result? Is it a win, a W for the first player? Is it an L, a loss for the first player, or is it a draw? Suppose we know this information for every vertex in this diagonal. Then the claim is that we can deduce for the next diagonal. It's pretty simple, because if we, for example, focus on these two vertices, so suppose they have labels, the labels that they can have are either WW, DD, WD, DW, or one of them is L. The star means any symbol among WLD. Then we can easily deduce the symbol for this red vertex. For example, suppose we know that both of these blue vertices are labeled W. Now the token is placed here. I am forced to move to the token to a vertex which is labeled W. And it is your turn now. Since it is labeled W, you will win. This means that I will lose here. Similarly, if it was any other combination, we can deduce precisely. So, and this reasoning was deterministic in nature, and if we add probability to it, we really get a PCA. In the sense that this vertex could itself have been a trap or a target. So that's how the PCA is, probabilistic cellular automata is being tied up to this game. And the authors used PCA to do the following thing, to establish the connection. So if we have a given distribution on the set of all possible configurations, then if we apply the PCA to it, this particular PCA, for example, we get a new distribution on the set of configurations. And this distribution mu is said to be stationary if it coincides, if the F mu is exactly mu. And they proved this result that suppose for every stationary translation invariant, reflection invariant, the precise meanings are not important right now, but I can come back to them later. Suppose any distribution satisfying these three things, we can prove that measure of the cylinder set D is exactly 0, which means that measure of the set of configurations which are D at the 0th coordinate. Suppose we can show that, then the probability of draw in the side percolation game is also 0. So this is their setup and this is the result they proved and how they did it. I mean, from this proposition, they use something called weight function method to deduce the final result. And this weight function method is precisely what I want to focus on today if I hopefully get the time. But before that, the game we study in this project is follows. It is a generalization of their game. So for them, there are traps, targets on vertices, and now we are introducing traps on edges. So we have three parameters, P, Q, and R. And again, we do a random process that every vertex is trap or target with probability P, and Q respectively. And now every edge is trap or open with probability R. That's what we do. And now the way the game is decided changes slightly, that if I move the token along an edge, which is a trap, I lose. And same goes for you. So one can even think that these edges go missing. So you are not even allowed. So, and if you reach a vertex from where you cannot move, you lose. So that's the setup. And this is the corresponding PCA that we obtain. Now, the point is that this PCA is, in its updation rules, pretty complicated than the PCA that was in their setup. So for example, as you can see, there are only 3 diagrams, but here there are 6 diagrams. The extra diagrams are coming from this L star star L condition being expanded. Just an example that LL and DL are give different updation rules because of the complications arising from this particular setup. And now again, we want to prove the same proposition using the setup which they had built, that for any stationary translation invariant and reflection invariant measure, we want to show that measure of D is 0. Now I want to take the next few minutes. There are 9 minutes, plenty of time, luckily. So I want to take that time to really explain how to do that using something we call as the weight function technique. I want to make an attempt to explain the weight function method here. At its core, the philosophy of weight function method is very, very similar to the following thing. Suppose we have real numbers x1 through xn, and we want to show that all of them are 0. One way to do that is to show such a thing. So to make them obviously 0, like from here they are obviously 0. So we also want to come up with an equation from where it follows that measure of D is obviously 0. I will first write that equation which we aim. It is weight of f mu minus weight of mu is equal to summation minus Ci, which are polynomials in P, Q, and R, and measure of cylinder sets I. I will try to unfold what this means. So first of all, this function which we are aiming at is just a I will write weight of mu, and weight of f mu will just be replacing mu with f mu. So weight of mu we are aiming at is just some finite linear combination. Oh, sorry. Yeah. It's a big room, sorry. So we are aiming for something like that. Weight of mu is a linear combination where scalars are coming from polynomials, and measure of the cylinder sets. By a cylinder set, I mean that at finite indices, we want the symbols to be fixed. So for example, W, L, D at 2, 3, and 5 respectively, and other indices can be anything. So that's a cylinder set. And we want something like this. Now weight of f mu will just be f mu input here. Now we see that what happens is, in the hypothesis, we had a stationary measure. So since the measure was stationary, weight of mu will be exactly equal to weight of f mu. So this side will be 0. And here we want Ci to be, here we have non-negative coefficients, non-positive coefficients because minus sign. So all of these cylinder sets, the measure of them will also be 0. So we obtain like this a bunch of measures which are 0, and we try to combine them to deduce that measure of D is 0. That is usually the easiest part. The crux of the difficulty lies in coming up with such such an equation, like making it obviously measure of d to be 0. And now I will try to see how we go about doing it. So for example, I can read off from there that so instead of EPQR, I'm just writing F here. So for that, or probably E here, that E mu D, for example, is, so it says that whenever D and W showed up, the probability of D appearing is 1 minus P minus Q times 1 minus R. So we have 1 minus P minus Q times 1 minus R, measure of WD. Similarly, for DL and LD, I will go ahead and really write it because I want to make a point. And 1 minus P minus Q, R 1 minus R. Okay. Okay. Now, suppose that, sorry, is there a mistake? Oh, yes. Yes, thank you. So now, suppose for a second that we pretend that this term and this term were not there. Suppose we pretend that for a second. Then if we took this weight function to be just measure of D, then we have obtained this part, right? And if we subtract this from that, then we have measure of, we want to subtract measure of D. But measure of D, we can write it like WD, LD, and DD, because you can just expand it, sum it up. All right. So now we are pretending that these are not there. So if you look at it, measure of WD, this is something smaller than 1. 1 minus P minus Q times 1 minus R, minus 1 will be negative. Similarly here, this is something smaller than 1. And here we don't have to pretend. So similarly here, so we would have obtained something like that. But since we are in real life, so there are these terms still there. So what we do is we start like this and we obtain these terms, and then we try to update the weight functions to handle them, and then we find tons of paths and ways of how to go about it, and then we probably take care of these terms, but then more troublesome terms pop up. We have to handle them, and as we go about doing it, hopefully this trouble ends. Sorry, sounds like life, but okay. And then the result we have is that for this particular game, there are epsilons, epsilon 1, epsilon 2, epsilon 3, such that whenever the parameters are smaller than them and they satisfy some conditions, then we have shown that the weight function can be thought of in that particular form. That is, the probability of draw is 0. So for those small parameters and satisfying these conditions, we have this result, for example. And the weight function we obtained is this. Like, yeah, it is this. Thank you.
Very much. Some questions?
Back to your theorem. So how, did you check that this region is non-empty?
Yes. Yeah.
Okay. So what is an example of a point in there?
Oh, sorry. I'll come back to you.
Okay. And how long? So when you say trouble ends, I suppose you mean that this stops in finite number of steps?
Yes.
Why? Can you give some intuition for why?
Yeah, sure. So the main thing is computation. Like, so for example, I wrote this expression, right? E mu of D is this. So there are 5 terms which show up, right? And if you look at, so for example, we have mu of LWD. And so we need to compute E mu of LWD. And there are 45 terms which show up. So, and if you want to go next step, the number of terms which show up is crazy. So, and we are doing it by hand. So, like that is the main thing which stops. And one more thing, that when we are doing these updations, that the region which improves is somehow not like it improves very rapidly first, but then the reward versus the cost also it's. Yeah.
Oh, I see. So there's some. Sorry. So there's some point where you don't get an exact kind of solution.
No, yes.
So you sort of get some bound at some point, which is good enough for you.
Yeah, probably there are better ways to do it. Like there are so many courses to go about, but probably there are better ways to do it. But this is in this computation. I don't know what is the computation cost. Like this is the result that we have right now, I would say. Yeah.
Okay. Thank you.
Any further questions? If not, let's thank Dhruv again.
Thank you.